Hello friends, today I am going to reveal some true facts of stardust. We are all made of stardust, but where does it come from? But first of all, I request you to please share and subscribe my channel for getting my informative true facts videos uninterrupted. Now, we are all made of stardust, but where does it come from? Next time you are feeling down, you beautiful things, just remember, you are made of stardust. Of course, so are fecal bacteria and serial killers. Not to mention the food you are eating, rust, arsenic, but even so, it is amazing to think that the materials in our cells once came from somewhere in the sky. But where exactly? Now, new research has uncovered patches of gas and dust where isotopes of some elements are more common than they should be, challenging that we know about their origins. Based on the makeup of the relatively young planetary nebula K447, researchers from the University of Arizona have proposed another method for the creation of atoms once assumed to have rather exotic origins. Most of the elements responsible for the complex chemistry behind life and geology are the product of various exterior reactions. Collectors enough hydrogen collect enough hydrogen in one place, and gravity will inevitably start to squeeze it into helium. In turn, helium is pushed together into slightly bigger elements such as lithium. To get even bigger elements to stick together, such as carbon and oxygen, you are going to need some impressive amounts of force, the kind found in the cores of massive stars, at least 8 solar masses at birth. Even then, some isotopes of these chunky buildings blocks are harder to build than others, though carbon-13 and oxygen-17 and nitrogen-15, for example, have an extra neutron pushed into their nucleus. It might not seem like much of the difference, but this innocent addition requires an extraordinary amount of grunt. The kind you had only find in the violet end of a star as it collapses itself is in an explosive supernova. Also, scientists figured, but it turns out that there is one niggling problem with these assumptions. The models invoking only novae and supernovae could never account for the amounts of N15 and O17 we observed in meteorite samples, said senior researcher of the study, Lucy Dairis. With an overabundance of such heavy isotopes during the rocks that falls to Earth, scientists have started to consider other explanations for the element's creations that don't require such rare astrophysical events. That's where K447 comes in. This cloud of gas and dust, 15,000 light years distance, is rich in carbon-bearing molecules, many of which are of the extra neutron variety. In fact, that we are finding these isotopes in K447 tells us that we don't need strange exotic stars to explain their origin, said Jaris. It turns out your average garden variety stars are capable of producing them as well. Stars such as our sun don't end their days in cataclysmic slime of hot, dense gas. In fact, like 90% of all stars, our sun will gradually expand as it loses mass. Its heat quietly puffing its atmosphere out into a red giant ball. The hot shell of gas then slowly drifts away over time to leave a bright white dwarf core. It might seem quiet, but one part of the dying process inside these rather common stars would be powerful enough to sow an extra neutron into heavy atoms before letting it drift off into the cosmos. As gravity loses its grip on the star's lighter outer atmosphere, helium continues to rain down on the core surface, raising its density and temperature. It takes millions of years to accumulate, but in a virtual snap of the fingers, a trigger point is eventually reached. Temperatures hits a crucial point close to 100 million degrees, allowing triplets of helium to form single atoms of carbon, shedding an insane amount of energy in the process. Far from acting like a gas, the electron deficient helium clings together like an ocean of liquid, trapping the rising heat. The result is what is known as a helium shell flash. A helium flash doesn't rip the stars apart like a supernova does. It's more like a stellar eruptions, says Iris. In the end, about 6% of the helium is converted to clean old carbon. For this supernova light to make isotopes like C13, however, the atoms need to also escape relatively quickly in order to cool down and not to force the undergo other reactions. The number seems to add up, but more examples would be help reinforce the model. The prevalence of these isotopes in K447 could also be explained if it was the result of a binary star system that shared an envelope of gas. One star of sufficient size could produce carbon before they merged, with a collision producing the nebula. A similar nebula called CK Bull is thought to be the result of such a binary white dwarf merger. It also has the same recipe of carbon and carbon isotopes. Tracing the origin of particular isotopes back to helium cell flashes could provide astronomers with a new way of interpreting the history of materials in our own solar system. You can think of the grains we find in the meteorite as a stellar ashes left behind by stars that had long died. When our solar system formed, says Jairus co-authors Tom Jera, we expected to find those pre-solar grains on Bennu. They are part of the puzzle of the history of the asteroids, and this research will help define where the material of Bennu came from. It might be as rare as we once thought, but it might be as rare as we once thought, but it doesn't mean isotopes like carbon-13 any less special. Maybe there is a lesson in there for all of us. In my next video, I will reveal some true facts of other more research on space. Thanks.